Welcome to today's video. You will remember that in one of the last videos we characterized local optima of multivariate functions. In particular, we found out that for a differentiable function, the gradient at a local optimum is always the zero vector. We have not yet found a way to characterize what kind of optimum we have here, and that's going to be the objective of today's video. To do that, we need to take a look at the second derivative. So from now on, we'll assume that our functions are twice continuously differentiable. So assume we have a function f that is in C2 of x for some set x. That is open. And let's say we have a point x star in x with the gradient of f at x star being the zero vector. The question is, how can we find out whether x star is a minimizer or a maximizer, or possibly neither of the two? Could also be a saddle point, of course. So how can we find out whether x star is a minimizer, a maximizer, or a saddle point? The answer to the question is we can use Taylor's theorem. And that's just what we're going to do. So Taylor to the rescue here. You will remember that Taylor's theorem says we can approximate a function f by its Taylor polynomials if it is sufficiently often differentiable, which we just assume for now. And that looks like this: f of x star plus the gradient of f at x star transposed times x minus x star plus x minus x star transposed times the Hessian of f at x star times x minus x star plus terms of higher order. So those involve x minus x star to some third degree. And what we know is these terms of higher order, these are close to zero if we are near x star. And what we also know is this specific point here, that nabla f at x star that is equal to zero because we have a stationary point. So that second term here vanishes, and that means the local behavior of f is characterized, well, of course, the function value, and then this quadratic term here. So it's basically governed by what this matrix does with the vectors here. Okay, and that's the takeaway message from Taylor here. So the local behavior of f at and around x star is governed by this term x minus x star transposed hf of x star times x minus x star. So, well, what can we say then? If we have an x that is close to x star, close enough, then x star is a minimizer if for all of these close x values, this expression here, if that is greater or equal to 0, because if that is greater or equal to 0, then the function value at x will be f of x star plus something positive, plus something that is close to 0. Okay, so if that expression is positive or at least not negative, then x star needs to be a minimizer. Otherwise, we could get function values that are lower. And of course, the reverse is also true. Okay, so let's write that down. If for all x in a certain neighborhood, so let's just say close to x star, either of the following holds. If x minus x star transposed hf of x star x minus x star, if that is greater or equal to 0, then x star needs to be a minimizer. And on the other hand, if that expression is less or equal to 0, then x star is a maximizer. Well, it's not quite true, actually. So we kind of ignored these terms here. And there is one edge case that we need to consider. What if this expression is actually equal to 0? Then, of course, these higher order terms will govern how the function behaves. So then we could not conclude it's a minimizer or it's a maximizer. Okay, so that is not yet quite correct. What we actually have to say is we need strict inequality here to be able to infer that. Okay, so equality might not be enough. Now this does look a little complicated. Before we look into that further and before we actually state the theorem on that result, we'll make a little definition to give matrices that have these properties their proper names. And in one of the following videos, we'll investigate methods of proving these properties without actually considering all possible x values. But let's start with that definition here first. So we'll start with a matrix. Let A, remember A is an n by n matrix, it's a Hessian. The functions that we looked at are at least twice continuously differentiable. So the Hessian matrix is always symmetric, and we'll assume that for matrices of that kind to avoid technical difficulties here. So let A be an n by n matrix that is symmetric. Then A is called, well, first possibility. We call a positive definite if this property here holds, basically, with strict inequality. So A is called positive definite if V transposed AV is strictly positive for all directions V in R to the n, with the exception of the 0 vector. Of course, it couldn't be positive if V equals 0. And just to complete that definition, there's also the expression of positive semi-definiteness, and that's the case if you also allow equality here in this inequality here. Okay, so it's called positive. Semi-definite if V transposed AV is greater or equal to 0 for all V in R to the n, with the exception of the 0 vector. Now, the second name, of course, if there is a positive definite, then there is also a negative definite, so that's defined completely analogously. So the matrix is called negative definite if V transposed AV is strictly less than 0 for all V in R to the n, with the exception of the 0 vector, and negative semi-definite if V transposed AV is less or equal to 0 for all V in R to the n, with the exception of the 0 vector. And finally, of course, there are matrices that are neither positive definite nor negative definite. So there are vectors where this product is positive, and there are vectors where this product is negative. And those also get a name to round things off. Those are called indefinite. So it's called indefinite if there are vectors v and w in R to the n, and again the 0 vector doesn't make a lot of sense here, such that v transposed AV is positive and w transposed AW is negative. And just as a small remark here, something that might be helpful in computations, a matrix is negative definite if and only if its negative is positive definite. Yeah, you can just multiply this equation here, this one, with -1, then you get minus the matrix if you take that sign into the equation on the left hand side. And of course the sign turns around if you multiply by something negative. Okay, so we have a greater instead of a less than. So a matrix A is negative definite if and only if the matrix minus A is positive definite. So, and finally, let's state our findings about the properties of functions with a positive definite or a negative definite Hessian. So that is the main result of this video. That's the theorem. As usual, we'll have x be a subset of R to the n that is open. We'll have a function f that is contained in C2x, so twice continuously differentiable. And we'll have x star in x. And also we'll assume that this x star in x is a stationary point. Meaning we require the gradient of f at x star to be the 0 vector. Then the following are true. First, if x star is a local minimizer, then the Hessian is positive semi-definite. It could still be 0, but if it's not, it cannot be negative definite. Okay? So that's the easy direction, so to say. If x star is a local minimizer of f, then the Hessian hf at x star is positive semi-definite. The reverse, however, is not true. Not necessarily. If the Hessian is positive semi-definite, then we need not have a local maximum. We need not have a local minimum. So what is true is if the Hessian is positive definite, excluding the semi case, then we have a local minimum. So if hf at x star is positive definite, then x star is a local minimizer of f. And of course, the same conditions hold for local maximizers and negative definiteness. So if x star is a local maximizer of f, then hf at x star is negative semi-definite. And part 4, if the matrix is even negative definite, excluding the semi case, then x star is a local maximizer of f. Okay, so we have characterized the types of optima, minima, and maxima using the second derivative. The condition is somewhat more complicated than in the one-dimensional case, where we just need to look at the sign of the second derivative. But again, we'll have a look at criteria for determining whether a matrix is positive or negative definite or indefinite in one of the next videos. Let me just mention that, analogous to that theorem in one of the last videos, the first order condition for optimality, this is now a condition that involves the second derivatives, and that's why this is called a second order condition for optimality. And this time it's actually not just a necessary condition, it also gives us a sufficient condition, at least the parts 2 and 4. Okay, so this concludes this characterization. Next we're going to see a few examples, and we'll have a look at how we can find out computationally whether a matrix is positive or negative definite or not.